Dear colleagues, I'm glad to present you our research and method of determining the fractal dimension of network traffic by its probabilistic properties and experimental research of the quality of this method by Hanna Drieieva, Oleksandr Drieiev, Yelyzaveta Meleshko, Mykola Yakymenko and Volodymyr Mikhav. During research and modeling information process in telecommunication systems and computer networks, it is necessary to take into account the fractal properties of telecommunication traffic. In particular, taking into account fractal properties significantly affects network traffic simulation, forecasts of load for network equipment, and detection of information texts. The known methods for determining the fractal dimension, such as rescaled range analysis or RS analysis, have significant errors and ambiguities in some cases, so it is advisable to develop new methods. Therefore, the task of improving the accuracy and ambiguity of determining the fractal dimension is a relevant task. Previously, there was proposed a method for determining the fractal dimension of network traffic by its probabilistic properties. Theoretical substantiations are given in the paper in the chapter 2.0. The main stages of this method are stage 1. At stage 1, we accumulate the binary time series for which fractal properties need to be determined. At the stage 2, we evaluate the probabilistic properties of the series, namely the occurrence of pairs of consecutive elements n00 and 01 and 01. And we obtain the probabilities lambda 1 and lambda 2, probabilities of change from state 0 to 1 and from 1 to 0. And at the stage 3, we determine the fractal dimension of a binary sequence by formula capital D of lambda 1, lambda 2, given by such formula. This is the main formula for our research here. Next, as the figure 1, the Markov chain for generating fractal binary traffic are presented, and the generator is calculated by states 0 and 1, and the probabilities P0 of and P1 for being in these states, and the probabilities lambda E, lambda 0, 1, 2, 3 of transitions. And accordingly, the first we need to generate fractal binary traffic. The algorithm for such generator we have here. At first we generate a series of random ones and zeros, the length of such series capital N, and generate random values from the interval from 0 to 1, and compare such values with probability lambda and inverse or not inverse the 0 or 1. And finally, we have the binary traffic of ones or zeros. To calculate the Hurst exponent, we implement the following program code in the Python 3 language. Calculate cum slots, construct a list of values, and calculate the Hurst exponent here. In the figure 3, we have the results of experimental measurement of the Hurst exponent at the vertical axis as a function of probability to save state lambda, and on the other horizontal axis from the steps of cumulative sums capital L. The behavior of the graph you can see here. The algorithm used for the experiment is shown in the figure 3. This algorithm takes an input the sequence to be analyzed and logs the values of shifts in the calculation of cumulative sums for each point of the graph which correspond to the probability of maintaining the state and range of lengths of cumulative sums. 100 times a random series of 10,000 values is generated for which Hurst exponents are calculated with the specific lengths of cumulative sums. The next graph shows the average values for this 100 and the graph of Hurst exponent as a function of lambda we have here with for cumulative sums of 1 and 3 samples with deviations of 2 sigma, minus 2 sigma orange and plus 2 sigma green. And for 100, 120 and 150 samples with deviations of 2 sigma. And in the proposed probabilistic approach, which is based on direct measurement of probability of state change from 0 to 1 and from state 1 to state 0, according to the formula on the slide 3 for capital D, for determining fractal dimension, which is implemented in the pattern language. The result of the research of the quality of proposed methods and in comparison with the well-known method of rescaled range analysis are shown on the next slide. And here we have the results of experimental probabilistic estimation of the Hurst exponent with deviations of 2 sigma. And numbers, the table for the results of quality comparison of methods for fractal dimension for the known rescaled range analysis methods and the proposed probabilistic methods PM. Here and here we calculated Hurst exponent H, standard deviation sigma, and deviations calculated by formula sigma divided by H, and the averages standard deviations for rescaled range analysis we have such values, and for our method values that approximate 3 times less, and deviations for rescaled range analysis method approximately 2.6, and for our probabilistic methods approximately 1.85. And conclusions, as shown by experiments on simulated network traffic, the proposed probabilistic method has great accuracy and unambiguous results regardless of the length of the studied series, in contrast to rescaled range analysis. Rescaled analysis, RS analysis, gives different values for different lengths of the cumulative sum, and the larger the step of the cumulative sum, the more different the value of the Hurst exponent determined by it. It indicates the ambiguity of the method and the possibility of manipulating the results by choosing the different lengths of the cumulative sums. The proposed probabilistic method does not have this disadvantage. The developed method is unambiguous and does not depend on the period of consideration because it does not use cumulative sums. Also, the developed method has a lower percentage deviation from the mean value that is the rescaled range analysis, which have 2.50, and the development has 1.8%. Thanks for your attention.